Okay, folks, here's the last segment now for today. And in this segment, what we're going to do is look at heat engines again. We're going to look at using an ideal gas as the system, the material in our heat engine. All right? And so if you remember from last week, it's actually this week for me, but last week for you because you're looking later anyway. Last week, when we drew a heat engine, we made a diagram that looked something like this. We had a hot area, a heat source. We had some circle that we called the system, right? And heat went in from the heat source. Work was done by the system on the rest of the universe. This is what we're trying to get out of this thing. And we paid a price because of entropy needs, and that is that we had some of this heat that couldn't be used to produce work, but had to go into dumping other heat into the heat sink, the cold side. You might call this thermal pollution, right? This is inefficiency of this engine due to the second law of thermodynamics, though, right? So what we can do is now, because we're going to use an ideal gas right in here as our system, we can start using our ideas of ideal gases and thermodynamic processes to see what we get out of this. As soon as we start talking about an ideal gas and the thermodynamic processes, we want to start drawing PV diagrams. All right? So here's one of those PV diagrams. Remember, P is on the vertical axis, V the horizontal axis. And now we're going to have a process that occurs, a thermodynamic process, that takes us from one spot to another. And we want to be able to do work. So let's do this simple process, right? A constant pressure process. Oh my gosh, I have succeeded wildly in doing what I wanted to do, right? In this process, going from, say, V low to V high, I have done work with my gas, right? Okay, there's an area there that tells me about the work. There's a problem though. The gas is now at spot number 2, right? Even though I've done work, the area under the curve, right? Now I've got this problem that I can't use the gas again because it's over here. To be able to use this gas in this system, it has to be effectively reusable. It has to be back where it started, at the end of everything. It has to be a cycle. All right, well, let me call this A. And now what I could do, because I have colored pens, is let me just go back and call that direction the B direction, right? And now I've done 2 processes. That's a cycle. So it got me back to where I was. What's the problem here? Well, look, as I move from here to here, the gas is doing positive work to the universe. You know that because, look, the pressure's remaining the same, but that piston got pushed up. There's a bigger volume in the container. So it did positive work on the rest of the universe during that process. Now, though, somehow the piston got pushed back down. Constant pressure, though. ooh, the universe did work to the gas, gave that work back. And look, the positive work going this way, the negative work going this way, have the same area under the curve. The total work that was done, 0. Yuck! Whatever heat that I put into this, I just did a 0 efficiency engine, because remember, efficiency of the engine is the work that I get out divided by, right, the heat that I put in. I put in heat to make things go. I got no work. This efficiency is 0. That's pretty crummy. Right? So I need to come up with a way to do a cycle where I don't end up with 0 work. All right? I can come up with a really easy one. All right? Very simple, very fast, very quick. Right? And so what I'll do is draw up this cycle first. Right? Let's make our PV area. Right? And now I'm going to go from 1 to 2, as I did before, with a constant pressure process. And I'll call this a P sub H for the high pressure. And here is V sub L for the volume, the low volume. Here's V sub H for the high volume. Now what I'm going to do is I'm going to come down with a constant volume process to this spot called 3. Then I'm going to go over here to this spot I'll call 4 with another constant pressure process at a lower pressure. And you can see what's happening now. I'm going to go back up with a constant volume process to end up where I started with, right, at spot number 1. So here is high pressure, low volume, some temperature. Here is high pressure, high volume, another temperature. Right? Remember those isotherms that tell me constant temperatures go like that. So I know this temperature has to be different from that one. This one, at the high volume, low pressure, is probably, well, it's definitely different from this one, the temperature. It's probably different from this one, unless I got really lucky to kind of scrape through there. And I could have arranged it that way, right? I could have done this process till I found this temperature, right? But what's up, I go to another spot with another constant pressure process. I'll be at P sub L, V sub L, and another temperature, right? It can't be either any of the other ones. So the temperature is going to keep changing on me, but I've got these, right, 2 volumes and 2 pressures to work with. The key here is, 1, it's a cycle. It gets me back to where I started. The other is, here is the area under the curve for this process. This process has no area under the curve, so we don't worry about that. This process, which is going to do negative work, has this area under the curve. It subtracts away from the first one. This process, no area under the curve. We can see what's in the box, enclosed in our cycle, is the area that represents work done. Right? There is the work that the gas gets to do to the outside world through this process. There's some that the outside world has to do back, and that's subtracted away to give me what the final work is that this does. So here is that work. Well, I can calculate what that work is, right? I can look at an isobaric process and work out what the work is for that, right? But it's really simple. All I have to do is calculate what the area is in that box. Well, look, the area in that box, right, is simply delta P times delta V. Or if I want to write it out, P high minus P low times V high minus V low. I've just calculated the work that this engine does during this cycle, right? Now, if I want the efficiency, then I have to go off, right, and calculate what the heat flow is for each of these processes, right? Can we do that? Sure we can, right? Let me pull my papers over here so I can kind of glance at them to make sure that I do the job right. So I'm going to do at least part of them for you, right? So let's call this A, B, C, and D. These lines are the different thermodynamic processes that I've labeled A, B, C, D, right? So let's look at what is QA, right? What is the heat that's going to flow into this system during this cycle? Well, it's an ideal gas, 1. It's an ideal gas doing an isobaric process, 2. In the first segment today, we figured this one out, right? It's NC for a constant pressure process, specific heat constant pressure, times delta T. There's a problem here. Delta T. I don't even know what temperatures those things are at, right? I mean, I know what pressure and volume. Ideal gas law. Maybe that'll, come to my aid. And in fact, if I glance down here, I see that it does, right? So what I want to do is change this delta T over into something that has to do with pressures and volumes. All right, so the ideal gas law, PV equals NKT, is going to come to save me, right? Well, remember, this is a constant pressure process, right? So V equals NK over P times T. So this is constant, right? So this parentheses, all that stuff is a constant. So this means that delta V is NK over P delta T. We actually did this before, earlier today, so I'm not going to go through final minus initial. Just write down the deltas. Right? Okay, so that means that delta T is going to be P over NK delta V, and now I can plug that in right there. Right? And that's going to give me volume changes and constant pressure stuff. Because this P is pH. Right? So at the same time, let me remember what CP is for a constant pressure process. Oh, that's going to be able to do work, and so I need the 5/2 NK. Right? So Q sub A is going to equal, here's the N still there. Now I've got 5/2 times N, times K. Right? 5/2 KB, right? And now I've got delta T. Well, delta T is going to be pH, P sub H, right, over MK times delta V. Well, this N and this N go. This K and this K go. So Q sub A for that process, right, is going to be 5/2 pH, the high pressure, times delta V, VH minus VL. Because H is the final and L is the initial. Look, we've got the first one done, right? Simple. We would go through, as it says right here, and determine each of these Q's, right? And what we would find then is that QA looks like this. QC we would do next because look, it's another constant pressure process. So I could use the same stuff. It's just what goes in for P and delta V. What I end up with is a minus 5/2 P sub L VH minus VL. All right, the minus sign comes in because the delta V goes from VH to VL. And so I flip the order so it matches with this. It gives me a minus sign. This right here is all a positive number. VH is bigger than VL, so the parentheses is positive. Pressures are always positive. Obviously 5/2 is positive. So Q sub C is negative. That means it's heat being dumped. This has pH, which is positive, VH minus VL, which is positive. So QA is heat being absorbed in to the system. So QA will be part of the heat absorbed. Q sub C, this is the C process, not cold temperature. It'll be giving off some of the heat, right? If I look at doing constant volume processes, we do the same thing, but there it'll be C sub V. We'll get 3/2 here instead. We'll have deltas with our pressures instead of our volumes. And what we end up with, if we do that, I'll look here so I don't mess it up. What we end up with is that Q sub D is going to end up being 3/2 VL pH minus PL, and Q sub B, which is the only one left, is going to be a minus 3/2 of VH pH minus PL. Once again, I've shuffled things around so that I can see this is positive, high pressure is bigger than low pressure, VL is positive, 3/2 is positive, this is a positive number, it's part of the inflow of heat. Here, again, the negative outflow of heat. And so if I want the efficiency of this engine, right? The efficiency of this engine is the work that I get out, the work done, which is right there, right? Divided by Q in, right? It's only the heat that goes in that gets divided, right? And so that heat in would actually be QA plus QD. And in fact, if I look at this, I could draw, here is some incoming heat. During this part of the cycle, heat is flowing out, right? During the D part of the cycle, heat is flowing in. During the B part of the cycle, heat is flowing out. We've created a heat engine here. We've used an ideal gas, and by using two different processes, two isobaric, two isochoric, we've been able to produce a cycle that gives us work done. All right, cool, or hot. right? Heat engine. Again, later on, if you laugh, it's still okay because we'll still say it's fine. Anyway, so here's how we analyze these things, right? Now, if we wanted to, we could add up all of the heats, right? If we added up all the heats, so that would be how much went in, and we'd be subtracting away how much went out. What is the first law of thermodynamics going to tell us? Well, remember, we've gone around this cycle. We've come back to this spot. Whatever the pressure, volume, and temperature were originally, that's what they are again. So that means that around the entire cycle, the internal energy of this gas hasn't changed. It changed along the way, but once we got back to the beginning of our cycle, it's back to where it was to start with. So during our cycle, this is true. That means from the first law of thermodynamics, right? That if I sum up all the Q's, that must be the work that the system did to the outside universe, right? To balance out. And in fact, that's what this diagram, remember when we drew them before, with a big thick thing here, and something here, and something, the thickness is all added together. Well, if I add all of these heats, that would be like positive coming in, the negative going out. What's left behind is actually the work that's done, and if you do that, you find out that that actually does end up being this value. I'm going to leave you to worry about those things, all right? Because it's just a bunch of algebra to do, right? So next, what we're going to do is take a look at other possible processes and the good and the bad with regard to that. Okay.